We now will give a short introduction to input-output automata as a review of what we are going to discuss in this lecture. So a distributed algorithm is specified as an input-output automaton. And what's an input-output automaton? An input-output automaton is a state machine that interacts with its environment. So input-output, or for short IO Automata, models concurrent interactive components, and they are suitable for components that interact asynchronously. Each input-output automaton is a reactive state machine. It means it has a state and it interacts with its environment through actions. And while it's interacting with an environment, it makes transition. And a transition, it means it moves from its current state to a new state through the action that it does with the environment. So it makes transition, and we have different classes of actions: input actions, output actions, and internal actions. So let us look to what I just said. So an input-output automaton can be described as a box which has state, and so this is input-output automaton A, and it interacts with its environment. This is the environment E through actions. And we have different types of actions. We have input actions. This comes from the environment. So this is input. We have output action from this automata. It can produce actions out. This is output. And it has what we call internal actions. Okay. So actions are named A1, A2, etc. And the interesting thing about an automaton A is that input actions are always enabled. In a sense, an automaton A cannot control its environment. So the environment, in this case like environment E, will output an action A, which always can invoke an input action A in the automaton. And for the system to progress, both the environment E and the automaton A make simultaneous transition. The simultaneous transition will change the state of the automaton, also the state of the environment. But the most important thing about input actions is that an automaton, in this case state machine A, does not control its input action. The environment that controls that. Then, as I said, we have a state machine or automaton has also internal actions and output actions. So in output action and internal action of automaton, they can be conditioned on A's state. So you perform the output action depending on its local state. And it can be blocked until the condition on the state becomes true. We say that the automaton A controls its internal and output action. We are going to see in the next units examples of that. This is just a quick overview. So what is executions? But output automata generate execution. An execution, as we have seen before, is an alternating sequence of state and action. You start from a state, say S0, you do an action A0, you move to a state S1, and so on. So what is fair execution? It is execution where the internal and the output action, these are actions controlled by the automata, are given infinitely many chances to run. So whenever an action is enabled, it should be given a chance to run. That's what we mean by fair execution. You cannot suppress such an action. So another concept we have is when we look to a distributed system or a distributed algorithm, we want to observe the behavior of that system. And if you consider the automaton itself or the system as a black box, what you can observe is external actions, input and output actions. So in general, interesting behavior of an IO automata is captured by its external action during an execution. So the sequence of external action we call traces. So a trace is a subsequence of fair execution where we just talk about the external actions. Okay, that consists of external action. And in fact, set theoretically or model theoretically, this set of all traces will capture the interesting behavior of an IO automata. So the behavior of this black box is captured by all possible traces it can produce. So given a problem P, if we design an automata A, we want to ask ourselves, what does it mean for an automata A to solve the problem P? A problem also itself, which is a distributed abstraction, will be defined by a set of sequence of external actions. So that is, of course, you describe this set by properties, and we will see that later. And an automaton A solves a problem P if the set of fair behaviors of this automaton is a subset of the set of all possible sequences or behavior of a problem P. So it means if here is the set of all possible behaviors of P, and here is the set of all possible behaviors of automaton A, then we say that A solves this problem. What it produces is consistent with the possible behaviors of the problem.